Hey folks, and welcome back. This is going to be the beginning of module number 3. This is going to be one of 2 lectures on computational thinking. So today in lecture, we're going to discuss what computational thinking is and how you can use it in life. All right, so to begin with, we're going to talk about where we were in the last few lectures. So we discussed how computers deal in binary. Everything is related to whether there's power on a line or no power on a line, or to phrase it differently, a 1 or a 0. A yes or a no. Everything is very black and white to a computer. Either it is a 0 or it is a 1. There is nothing in between. And so the way that computers work is that you have these gates that we talked about, the logic gates, like the AND gates and the OR gates. And when you add those together with the wires that allow power to move back and forth, you can build a rudimentary machine that is capable of adding a couple of numbers together or multiplying a couple of numbers or doing stuff like that. And in the beginning, that was an amazing invention. Just being able to add numbers quickly without people having to use like an abacus or write it down on paper and do it longhand, all of a sudden you could process large amounts of information very quickly and you could get back an answer. So computers were revolutionary just as a calculator. But then people started to wonder, well, okay, that's great that they can do financy kind of stuff, but is that it? Can we do any more with it? And over time, people realized that they could do bigger and bigger and more complicated things. And of course, today, between your phone, your computer, and everything else that you have in your life, you know that computers are capable of doing remarkable things, which are way more complicated than just adding 2 numbers. So, what's the middle ground between the binary numbers and the logic gates and that game that you just bought, that you spent $50 on, that's capable of drawing an entire world and allowing you to interact with characters and do all kinds of crazy things? And the answer to that question is software. Software is computer programs that somebody wrote that do complex things under the covers of a computer in order to let you see a more amazing thing that you are used to at the moment on your computer. And so, to be clear, their middle ground started off with just doing the little basic math things, and then eventually they figured out that they could do more complex math. They could do formulas, and they could write little bits of software that could do more than just add 2 numbers. For example, calculate interest. If you're doing compounding interest, it's not something that you can just calculate. Usually you've got to apply a formula in order to figure out how much it's going to be over time. And so you can write a piece of software that does that, and then you have something that allows it to calculate interest. And then you can figure out how much the taxes are, and you can write a program to do that. And you can keep building more and more complex things on it. And eventually you end up with spreadsheets, and you end up with more complicated mathematical formulas that it's capable of solving. And at this point, you've probably run into, if you're an engineering type person, into Mathematica or any of these kinds of programs that can solve pretty much any math problem that you give it. It's just given to the computer gives you back an answer. It's kind of amazing. And then over time, they realized, well, could we use a computer to output graphics on the screen? And yes, we could. And so in the beginning, that was very rudimentary. Like think about something like a Pac-Man or a, Space Invaders or something like that. It's just little dots and squares and circles that are running around on the screen, and you're able to move things. But that was the beginning of people saying, okay, well, if we can do that, can we make the circle 3-dimensional? And can we apply shading to it to make it look a little bit more rounded and have lighting that comes from one direction and the other side is darker, and that'll look a bit more realistic. And over time, those advances just got better and better and better until we ended up with where we are today. So what I want you to get out of this slide is that software is the bridge between that very rudimentary low-level machine that's able to add a couple of numbers together, subtract a couple of numbers, and do very basic things like that, and the complicated pieces of software that you have used in your everyday life. On your phone, every application that you've ever run, every game that you've ever played, they are all software that some human beings sat down and wrote to make a computer understand exactly what it is that you want it to do. So, what is software? Software is a computer program, and computer program is a bunch of instructions that are very specifically written to make a computer do a specific task. Computer software is written in a specific programming language, and there are many different programming languages out there. For example, later in this lecture, we're going to begin to see Python. We're just going to see a little snippet of Python. And then later in this course, we're going to deal in Java. If you move on to later courses, you'll see C#, you might see C++, and you might see other stuff as well. There are many different programming languages. This is not all of them. As a matter of fact, it's a very small subset of them. New languages come around every few years when people want to do something different, but in the end, they all have the same purpose, which is to take an algorithm and implement it for a computer to understand. Each of them has pros and cons, and so it's not like one of them is the perfect language for everything. Some things are better suited to some problems, other languages are better suited to other problems. So different languages exist for a reason. Also, developers just get used to one language. I will say, as a developer, if you're wanting to go down this path, don't be that person. Get used to the idea that over time, languages will change. Every few years, people will start wanting to play with a new language, and older languages will start getting deprecated. So while a lot of people code in Java today, a lot of people code in C# today, and a lot of people code in Python and C++ today, at some point in the future, that list will probably be different. There'll be newer ones on there that people like more. And already many of those ones are out there. They're just not maybe as popular yet. So don't get hung up on one language. The truth is, once you know how to program in one language, programming in others is really not that difficult. Each language implements, each implementation of a particular algorithm is a implementation of a human design. So what I mean by that is every game you've ever played, every application you've ever opened, every software that you've ever used is a computer implementation of something that was written by a human. You're interacting with software that some human sat down and wrote. And the way that they wrote it is that they decided, this is what I want this application to do. So when you open that new game, and it begins with a credit screen and it tells you what's going to happen in a world far away from Earth, blah, 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 whatever's going to go on. All of that, somebody sat down and designed it. They said, when you sit down for the very first time to play the game, this is exactly what's going to happen. And then you're going to end up in this room. And then these bad guys are going to approach you. And then you're going to have this battle. And then you're going to move on to this next room. And then you're going to have a battle there. And then you're going to pick up some gold. And then you're going to get stronger. And then blah, 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 blah. Somebody designed all of that. Every detail of what's going to happen, somebody had to sit down and design. And so this is the harder part of writing software. It's coming up with exactly what it is that you want the software to do and exactly what you want it to do at each individual point as it is running. So every single application, every program, every website you've ever been to, they were all designed as an algorithm, and then they were coded in a specific programming language. And that programming language then made it machine executable code, and the machine is just executing it basically the way that we saw it's able to do that with the AND gates and the OR gates. So you're going to find that there are some parts of writing code that are easier and some parts that are going to be harder. Writing code is very different than what you have done before now, unless you've ever written code before. So when you're speaking to a computer, you have to be very, very specific. For example, if I said to you, would you like to get lunch? You'd understand what I mean is that we're going to meet up, go somewhere, get some food, we're both going to eat it, we'll probably talk, and then at the end of it, we're going to go our separate ways. But I said only 3 words. You want to get lunch. And somehow you interpreted all of the detail out of that. If I was telling that to a computer, it would have to be a lot more detailed. I would have to explain what it means to eat. I would have to explain what it means to meet up with somebody. I would explain exactly what it is that you're going to have to talk about while you're eating that lunch. So all of those details have to be given to the computer. Computers do not just make up vague answers or take vague things and understand them. They have to be told exactly what it is that you expect them to do. And this is very different than anything that you've probably ever had to do before, because you're used to a certain level of abstraction, which is a word we'll talk about later, where you can just say something at a high level and you expect people to fill in the details. Computers will not fill in the details. You're going to have to think through all the details and tell it step by step what it is that you want it to do. Once you have actually decided what it is that you want it to do, actually converting it into a programming language is really not that hard. Each programming language only has a few hundred keywords. Unlike English or any other language that you may know that's a verbal or written language, there are thousands of words you can use in English. There really aren't that many words in Java or in any other language that you might look at. So each of the programming languages are actually relatively easy to learn. You're going to notice that the syntax is usually not the hard part. The syntax is just the detail of exactly what words have to be written in what sequence in order to tell the computer to do something. Some of it's going to be a little non-intuitive, but even most of the syntax reads like English. So you're going to look at it and go, okay, I kind of understand what it's asking the computer to do. It's meant to be readable by a computer and also by a human. So programming languages are a middle ground where a computer and a human can speak. And they're very specific because the computer needs to be very, very specific, but they're actually relatively simple. So the hard part of being a programmer is not writing code. The hard part of being a programmer is figuring out exactly what you want the code to do. Or to phrase it differently, to come up with the algorithm that you want the computer to execute. Then you convert that algorithm into a language, and that language has all of the syntax and all of the details that you need. So the hard part of solving a problem is problem solving, which I know is a bit roundabout. But a large part of what you're going to learn in this class is how to take a problem and how to solve it. And that seems like a very simple idea because you problem solve at some level in your life all the time. But in order to be a developer or somebody who's writing code, you have to learn how to specifically be able to solve any problem and explain it in enough detail that a computer is going to be able to do it. So, problem solving and then coding are the tasks that a developer does. So, the first step to problem solving is to take something and break it down. Let's talk about this. If I ask you right now to go build an airplane, you probably have no idea how to do that, because I have no idea how to do that. How do you build an airplane? Well, there's a lot of stuff in there I don't know. And it has to fly. And there's engines, and there's fuel, and there's wheels, and there's all kinds of drag and performance, and the shape of the wing is important. I don't know. And so, a lot of times, if I were to pull a student up and say, design me an airplane, they would shrug and go, I don't know. And that's no good. Can't do that anymore. Sorry. Even though you don't know how to build an airplane, there are parts of an airplane that you do know how to build. For example, the airplane has wheels. You've seen wheels before. You know that they're round. You know that they have tires. You know that they have a metal insert in the middle that holds the tire in place. You know the tire is filled with air. So there are definitely questions you would need to ask about an airplane tire, like exactly how big does it be and what kind of forces does it need to be able to take and what particular type of rubber do you use for the tire and things like that. But you do not know how to build a wheel for an airplane. And likewise, if we take this big problem of build an airplane and I break it down into a lot of smaller problems, you can start to see that some of those problems, although you may not have the immediate answer, you at least have an inclination as to how to start problem solving. So, for example, an airplane is made up of what parts? Well, there's the part that you actually sit in, the fuselage, right? That's the big tube looking thing that has all the seats. And upstairs you have the people, and downstairs you have the luggage. All right, so that seems like a big tube. I'm sure there's a lot more detail that we're going to need to figure out about that, but let's go with the tube. Are there windows? Yeah, there's windows usually in airplanes. Do they have to be there? Well, if you're going to have people, probably so. Those windows are going to be very specific, and I'm going to need to talk to some engineers about how to put windows in there. Next step is we know that the airplane has some wings. And I don't know the details, but I know that there are two, usually. There might be two more at the back for whatever reason. And I know that the wings are basically shaped where they're kind of rounded on one side and they're smooth generally on the other, and they have parts that move in and out because I've seen that because I've sat in an airplane and looked out the window. Um, so I don't know all the details, but I know vaguely what makes up a wing, and I know it's pretty big. So if we're going to build wings, we're going to have to find a big factory to build wings. I also think they put all the fuel in the wing. So basically, the wing is a big tank, and that we're going to have to figure out all the details of that. All right, so that explains where the fuel goes. So now we're going to need to figure out where the engines go. Well, they're usually hung off the wings. Okay, so the wing has to be strong enough to hold engines, and those are probably going to be pretty heavy. And then we got to talk about how the engine works, right? So I know it's a jet engine. Everybody says jet engine, so it's probably a jet engine. What does that mean? I don't know. Let's go to Wikipedia. So my point here is, although I don't know how to build an airplane, just with a couple of moments of thinking about it and not giving up, I'm able to break it down into smaller chunks. I'm able to say, well, I'm going to have to figure out the wing part. I'm going to have to figure out the fuselage part. I'm going to have to figure out the wheels. And I'm going to have to figure out the flight control systems, right? The pilot sits at the front and they press buttons and move knobs, and somehow that makes the plane fly. And all of those are details that are going to have to be worked out, but I at least now know how to approach this. I need to go find somebody who understands how wings work. And I need to go find somebody who understands how the fuselage is built. So I go and I engage engineers who know that kind of stuff. Or I go Wikipedia, or look it up online in some way. My point here is I didn't just give up and say, I don't know. I started to take the big problem and I broke it down into smaller, more manageable problems, and then I took each one of those problems and started to go solve it. And although I may not get very far with this, I don't think I'm going to be able to build a plane today. I know I'll at least be able to get to the point where within a couple of weeks, I could tell you the detail of how long it's going to take to make a plane, right? And then from there, I'm still going to have months and months and months of engineering work and planning and all the rest, but I believe I could solve it. Even though I'm not an aeronautic engineer, I'm the type of person who can take a big problem and can solve it by breaking it down into smaller problems until I get to something that I can understand. And I can ask for help along the way from the people around me who may know more about individual parts of that. If I go to individual people and ask them, help build an airplane, they're going to go, well, I don't know. But if I go to them and say, I know you're a wheel person, I need help with building a wheel for an airplane, they're going to go, okay, well, how heavy is the plane? I don't know. Let's start doing basic math. How heavy is a fuselage? How heavy is 400 people? How heavy is all the baggage? Put those together, and that's a rough estimate as to how heavy the plane's going to be. Well, okay, throw in some fuel. How many gallons of fuel do you need? I don't know. A lot weighs a lot. We can come up with a number. My point is, you don't solve problems by going, oh. So you need to stop doing that. You need to take the problem and say, I'm going to find a way to get to a solution. Regardless of what it is, I'm going to keep working on this until I get to a solution. And then break it down into smaller and smaller and smaller chunks until you can actually start solving things. Ignore all of the detail. So, what color should the wheels be? No. In that case, I really don't know. They seem to usually have black tires, but the center of the wheel, I think, is usually silver. I have no idea. It's an unnecessary detail. The reality is, it probably doesn't matter what color the wheel is. It can be bright pink and it'll probably still function. There may be reasons why you don't want a bright pink wheel, but we can deal with that later on. When you're breaking it down and trying to find solutions, don't think about every little detail and don't get stuck on one detail. Just throw away all the unnecessary bits and focus on the parts that you can solve. And that's a very important skill in life. If you have a big, complicated test, don't focus on one question that you don't know how to answer and then cry and decide that you're going to fail the test. Instead, skip it. Move on to the next question, solve it, work your way through the other problems, and then come back to the really, really hard one and see if there's a part of it you can get partial credit on. Even if you don't know how to solve it, get part of it done. Because that part may then help you figure out what the next part is. Oh, okay, if I get that, I see how you get this. That's how you problem solve. You keep breaking it down and you keep ignoring details until you can find a part that you can solve. And then once you do, you come back and you solve it. All right. The last step that's on here is recognizing patterns. So at some point after we started building the plane, I'm going to have to attach these wheels that I've built, right? How do you attach the wheels to the plane? Well, I think they hide in there's a little door underneath, right, that opens up and then the wheel comes down and then it lands, and after landing it comes back up and the doors close. All right, so there's some kind of mechanism for opening and lowering that. There's mechanisms on the wings for moving flaps and all kinds of other things on the wings. So there's going to be some hydraulics, things that are moving big mechanical pieces like the wheels and the flaps on the wings, and I'm going to need to know how to do that multiple times. So recognizing that there's multiple different smaller problems that share things in common is another great way of making progress on a big problem. At some point, I need to take the people who are dealing with the wing and the people who are dealing with the wheels, and I need to put them into a room together and say, y'all both are dealing with hydraulics. Make sure you're being consistent. Make sure you're solving the same problem with the same solution. And so recognizing that things are similar will allow you to, A, find solutions for things you don't understand because you understand some other thing and it's similar enough that you're able to apply one answer to the other. And the other thing is, it also allows you to consolidate problems and say these are really all the same problem. Once I solve this one, they're all actually solved. So recognizing that you have the same question or recognizing that they share a similar answer is an important part of problem solving. All right, so problem solving is taking something big and complex, breaking it down, ignoring unnecessary detail, don't get hung up on it, don't give up, and just keep solving individual bits. And that is what computational thinking is all about. It's about not getting overwhelmed. It's about taking something and breaking it down until you can get to something that is solvable. All right, so we're going to take an example. Let's imagine that I pick you up and I drop you into New York. And I ask you, you're currently on Wall Street, and I ask you to get to Rockefeller Center. Go. Assuming that you've never been to New York, you're probably like, I have no idea how to do that. But I tell you, hey, here's a subway map. Subways are trains that get you all over the city. Figure out how to get from Wall Street to Rockefeller Center. And I go one step further, I at least show you where Wall Street is on the map. So I put an arrow right here, and you can see there's Wall Street. And up here, I put an arrow for Rockefeller Center, and you can see it's right up there. So it's about halfway up the Manhattan Peninsula from Wall Street to Rockefeller Center. All right, so go. How do you solve this problem? So we're going to do two things. Not only are we going to find a solution to this particular problem of how do I get from Wall Street to Rockefeller, but I want a more general solution of if I give you any two locations, tell me how to get from one to the other. So let's first start off with the current problem. Wall Street to Rockefeller. So if you look at this map, you can see that a lot of the train lines, all the train lines, are different colors. We've got a red line that comes across here. We've got a blue line that seems to go across like this. We have orange lines, we have yellow lines, we have green lines, we have purple lines that go across this way, we have gray lines that go across this way, and so on and so forth. Lots and lots of different lines. So the first thing to notice is that Wall Street, which is where we're starting, turns out to be on the red line. Now, there's a lot of detail here that we could talk about how the train systems work in New York. None of that is really relevant. The lines generally have numbers and names, and the numbers and names usually correspond to colors. So red in this case is the 1, 2, 3 line. Different destinations is usually what the 1, 2, 3, or different times of day that the trains run on. Other lines are letters, so like A and C is the blue line in this case, and the green line runs up here as well. So we're just going to talk about them as colors because that's what the map shows. So we're not going to worry about the letters and all the meanings of that. And I agree that there's all kinds of details that we need to figure out, like how do we get on a train? How do we pay for a train? Where do we get on? Where is the actual station on Wall Street? Blah, 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 blah. None of those details matter. Shut up. So now we're just going to talk about, assuming that we are in Wall Street and we know how to get into the red line, how do I get to Rockefeller Center? Okay, so let's trace where the red line goes. So if we go this way, it goes off the map over here, and that's going in the wrong direction from Rockefeller. So I don't think that matters. So ignore everything to the right. So instead, we're going to go the other way. If we follow the line around, we can see that it travels up here, and it doesn't actually get me to Rockefeller Center. It looks like it goes off the map at the top right up here, but I'm close, but I'm not actually where I need to be. I'm just kind of off to the side of it. So again, this is where I'm trying to get to, and the closest I ever got was like right in here, which is close, but it's not quite where I needed to be. All right, so step one, I took my source, which was Wall Street, and I followed whatever line it was on to see if I happened to randomly end up in the destination. And it turns out I didn't. So that's not great. It's going to be a little more complicated. All right, so let's take a look at the next problem. Let's look at our destination. So our destination is in Rockefeller Center, which is right here, and it appears to be on the orange line. So if I follow the orange line, let's see how close I get to the red line or to Wall Street. And it looks like the closest I ever get is really not that close. I'm actually quite a bit north of Wall Street here. And the other problem is on the orange line, there doesn't seem to be a lot of stations. Stations are depicted as these circles. So there's a station at Rockefeller, and there's a station at 42nd and 34th and 23rd and 6th Avenue, and there's one here at 4th Street. But then there's not another one till here, then here, then here, here, and then we're off the map. So there's only a handful of stations, and none of those got me anywhere near Wall Street. So I tried working forwards from Wall Street to see if I could find Rockefeller, and I couldn't. I tried working backwards from Rockefeller to see if I could find Wall Street, and I couldn't. And I've realized now that the problem is Wall Street and Rockefeller are on two different lines. One is on red, one is on orange. And those two lines don't ever actually intersect. I never see a place where there's an orange line and a red line, except right here, that cross. And the problem with right here is there's no station there. That just means that under New York, there are two places where the trains just happen to cross each other, but in reality, they don't actually have a station there. So I can't get off the red line here and transfer to the orange line. I can only do that at places where there are stations. So how am I going to solve this problem? Well, I still need to figure out how to get from Wall to Rockefeller. So since the two are on different lines and the two lines don't overlap, I'm going to need an intermediate line to get me back and forth between them. So let's start off at Wall Street and let's walk our way up towards, let's get most of the way up there and then figure out how we can transfer. So let's stop here at Times Square, 42nd Street. This one seems to be a connection of a bunch of different lines. The red line, the purple line seems to connect here, and also the yellow line seems to connect here. So let's try each of those one at a time. So we're on the red line, so let's look at the purple line. Well, if I go this way, I'm going away from Rockefeller, so that's not right. So obviously we go this way. And yeah, that seems like it's working. I'm getting real close to Rockefeller, but you notice there's no station in there. As a matter of fact, there's still no station. The first station is going to be right over in here. So it doesn't quite get me to the orange line. The next station is here on the green line, and that doesn't really get me to the orange line either. So this purple line does kind of go where I want to go, but it doesn't actually get me to where I'm trying to get to. So I don't think we're going to use the purple line. The other option that we had was the yellow line. It also intersected with red here at 42nd Street. So it looks like I can go north, and I do cross the orange line, but again, it's just a crossing. There's no station there, although there is one close by. But if I go south, it looks like there is a station here at 34th Street that I can get off and transfer to the orange line. Okay, so I found my first solution. I go north on the red line until I get to Times Square. I get off at Times Square and I go southeast specifically on the yellow line for one stop to 34th Street. I get off and I transfer to the orange line and I go two stops and I get to Rockefeller Center. First solution. All right, is this the perfect solution or the right solution? I don't know yet. I'm going to look and see if there are other choices. It seems reasonable. It looks like I've gotten there, so we're definitely going to write that one down as a possible solution. All right, so let's look at other choices. Well, if we look carefully at Times Square, there's also this weird little black line that connects between here and here in a V shape. And there's a little note underneath it that says, transfers 6 a.m. to 11:59 p.m. only. So I'm not really sure what that's all about. But it looks like somehow I can get off the red line, I can take this transfer, and it'll bring me to this 42nd Street connection, which I can then walk take one station north to Rockefeller. So instead of transferring to yellow, I can do this transfer. Now, that is a valid solution, but I'll be honest with you, not being from New York, I don't really know what that means. Like, what is that transfer? Is there a specific place in the station I have to go? Is it a bus that I have to go out on the street and get on, and then it brings me to the next station? Or is it just another train line? And if it's a train line, well, which line is it? It's labeled black. I'm pretty sure there isn't a black line. So I don't really know what that means. It looks like it's a solution, but it looks like it's maybe a complicated solution. So I'm going to note that it's a possible solution, but so far I'm liking the first one better because it's more direct. Well, it's not more direct, but it's more clear as to how it would work. The other thing I'd have to be careful about is what time of the day am I trying to get from Wall Street to Rockefeller Center? If I'm trying to get there at 2 p.m., then this transfer is an option. But if I'm trying to get there at 3 a.m., it's not an option. So I'd want to be careful about stuff like that. This is input to my algorithm that I need to tell. Not only do I need to tell the algorithm where I'm starting and where I'm going, but it turns out I may also need to tell it what time of day and maybe even what day of week I'm going on. Another thing that might determine which way I want to go is the weather. So let's explain that just a little bit. If I follow the red line north, you'll notice that even if I never got off at Times Square, the very next station is 50th Street. And if I look at this map, it looks like 50th Street is actually the street that Rockefeller Center is on. So I'm only actually a block and a half away from Rockefeller at that point. So one valid solution might have been just take the red line north, go to 50th, get off and walk a block and a half. And that will be a perfect solution, unless the current temperature is negative 15 degrees with 100% wind chill and there's 6 feet of snow on the ground, in which case I probably do not want to do that walk. So, depending on the weather, I may have different opinions. This transfer to the yellow line may be a very worthy thing to do if it's really, really cold outside, or really, really hot, or if it's storming, or there's a hurricane, or something else that's happening in the city. So the weather is another data point that I might need to fill into this algorithm, because the correct way to go may be determined based on the time of day, the day of the week, and the weather. Other things that may need to be passed in are there any scheduled outages on any of the system? Is the red line even running today? Anyway, okay, so we found 3 solutions so far. 1, we can take the red line north to Times Square, take the yellow line southeast, transfer at 34th, and go north to Rockefeller. Works. 2, we can go to Times Square, take this weird transfer thing that we're not really sure about, the 42nd, and then go north to Rockefeller. Looks good. 3, we can just get off at 50th Street and walk a block and a half. Boom, we got there as well. Are there other solutions? There absolutely are. One interesting thing to notice is that there's actually 2 different Wall Street stations. I pointed you only at the one on red here, but there's another one all the way over here that looks to be on the green line. So it's actually possible that maybe you could have gotten on the green line one and gone north, and although it doesn't bring you directly to Rockefeller, it gets you pretty close. And even if you didn't want to go all the way up, it looks like you actually can transfer off the green line onto the orange line at Blacker Street. So there was maybe another option there. To be honest with you, there are many, 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 many options you could find. It turns out in this subway system and in most subway systems, there's going to be lots of different ways to get from one place to another. They build the system with redundancy built in so that in case there's a problem on one line where the train is stuck or the electricity is out or whatever the problem may be, people can still get where they need to go by taking another path. And it's not just train lines that are built this way. Roads are built this way. Everything is built this way, right? We don't want just one path to get from point A to point B. You need lots of options. So hopefully when you're trying to find an algorithm to get from one place to another, you are trying different options. Okay, so we have found a couple of ways to get there. We have found a solution to the very particular problem of how do you get from Wall Street to Rockefeller Center. But let's talk about the more general question, which is, how did we actually go about doing this? Well, I started by noticing that the Wall Street station is on the red line, or the 2-3 line. I then noticed that Rockefeller Center was on the orange line, or the BDFM line. Since they're 2 different lines, I then have to find a place where they overlap. It turns out that they don't directly overlap, so that means that I have to find an intermediate line that takes me from one place to the other. And so I eventually found a solution that way. So I have found a solution, or 3 in my case. Which one of these is a good solution? Well, let's talk about goodness, or the goodness of a solution, or the correctness of a solution, or the betterness of a solution. This is a very weird thing to say, but in computer science and in problem solving, what's most important is that you find a solution first. Don't worry about the details of is it the best solution or the only solution. As a matter of fact, for most things that you're going to write in this class, there are going to be many different ways that you could have done them. If I picked you all up and transported you to New York and dropped you in Wall Street and did not let you talk to each other, the chances are you'd break up into many different groups and you'd actually end up going different ways. Some people may decide, I just don't like the subway, I'm going to walk. Some people may take a taxi. Some people may have very creative solutions. So there are many different ways to solve the same problem, and don't get hung up on which one is correct. Just because your buddies all went and did one path doesn't mean it was the best path or the right path. It just means that's the one that made the most sense to them. You'll see that quite often as we look at algorithms, sometimes one algorithm will make sense to one person, but a different algorithm that solves the same problem will make more sense to another person. And this is true even for us, the instructors. Every now and again, we teach things that we're like, that's one that never really made a lot of sense to me. There's another solution that I know how to get to the same answer, but it's for whatever reason, we have to teach both because some people know one and some people know the other. So don't get hung up on the correct or the best solution. There are classes that you'll take later on in your degree if you continue down a computing path where you will talk about the efficiency of an algorithm or how well an algorithm works or how quickly it works or how much resources it uses. All of those are discussions for later. They're not discussions for today. Today, your solution is finding a solution. Having said that, you also have to make sure that you're meeting all of the criteria that people give you. So there may be specific data that you might need to take into effect when you're coming up with your algorithm. And we talked a little bit about this, like, is the train line running? Is an important detail. If it's 4 o'clock in the morning, some of these lines may not be operating. And so you need to know that if it's 4 o'clock in the morning when you're trying to get from one place to another. So a given solution only works if it actually works. It meets all of the criteria that you were given. And so you do need to evaluate, did you do everything that you were asked to do, and will it work? Different people may have different criteria. So some people do not like crowded stations and crowded trains. And for me, it's not a problem, but for some folks, being in a crowded train is very claustrophobic. And so it may be that if you ask locals, they may tell you, well, this line's way busier than that line. You might be able to take the other line and have a less crowded train. So just be aware that there are other criteria that are being used by different people. As far as the efficiency of the algorithm, this is not your primary concern. But I will point out that there are obviously terrible answers. For example, take the blue line AC to the JFK airport. Okay, well, it turns out if you follow this one way or another for long enough, you'll eventually get to the airport. There's multiple airports in New York. JFK is one of them. Another one is LaGuardia. So one path to get between Wall Street and Rockefeller Center is take the blue line to JFK Airport, fly to Sydney, Australia, fly back to LaGuardia Airport, take the purple line to Grand Central Station, walk a block. Okay, that does work, and it does eventually get you there, but it will take you 3 days. And you'll be exhausted, and also with multiple thousands of dollars. And really, there were better solutions. So I know I've just said two contradictory things. One, which was, don't worry about the efficiency of something right now, but there's an upper limit to that. If it gets ridiculous, then you need to find a better solution, and that's clearly ridiculous. But if you found a solution that sent you one extra station in one direction, good enough. That'll work. And as I said earlier, in the end, if this was actually me, and you dropped me in New York and asked me to get from Wall Street to Rockefeller, what I'm going to do is I'm going to take the red line, I'm going to get off at 50th Street, and I'm going to walk. The reason I'm going to do that is because that's an easy, simple to understand algorithm. And I know I'm going to get there without having to figure out how to do a transfer from a red line to a yellow line and accidentally go the wrong way, because sometimes they're not labeled east, south, north, and west. Sometimes they're uptown and downtown, and I may not know what all that means. And I know that I can get out of a station and walk on a street, and I can figure it out to get from there to there. Because realistically, if I've gone a block and a half and I haven't seen it, I'm probably going the wrong way. Also, if you see the ocean, probably the wrong way. So there's some easy ways that you can use the real world that I would prefer to figure out rather than try to figure out the intricacies of the train station. But that's me. Different people may have different requirements or different criteria for figuring out what they want to do. Okay, so for most problems, there may be many solutions. Don't worry about finding the right one. For now, just focus on finding a solution. Notice that many of the lines and stations on the map were never even looked at. We ignored the purple line. We ignored the gray line because they're not relevant. It turns out the yellow line is not relevant either for the most part, except for that one connection. So you don't want to spend time looking at every detail of this map in order to understand everything. You just focus on the thing you're trying to solve and ignore all of the other details. So that's an important thing to do. Figuring out how you can throw away parts of the information that you don't care about. All right, so in the end, our algorithm for navigating the subway. Figure out what station you're at and what line it's on. Figure out where you want to go, what station is closest to your destination. Figure out what line that station is on. If they're the same line, get on the train and go. Stop looking for other solutions. If they're not, then find something that connects the two. A third line, possibly a fourth line, maybe even a fifth line, but if you get to the fifth line, something has gone probably horribly wrong. What I mean by that is, in most transit systems and in most roads, If you're having to change 2 or 3 times, that's plausible. But if you're changing 5 or 6 or 7 times, you're probably doing something crazy, because the systems overlap enough that you shouldn't have to do that. So there comes, and this is kind of like going to the airport and flying back, there comes a point where you realize you've probably gone down a wrong path. If it's getting way, way, way complex, then overall you probably need to look for other options. If you have found a solution, you go, you transfer at each connecting point, and eventually you'll get to your destination. So this is a general algorithm for navigating subways. In this case, we dealt with the New York subway, but I could now take that algorithm and take you and transport you to London and drop you in the London tube system. And as long as I give you the map from the London tube system, which looks quite different than the New York one, you could apply that same algorithm and know how to get from silly named places like Piccadilly Circus to somewhere else in London. And so a tube map, a subway map, a transit map from any city, Berlin, New York, Chicago, all the way out in Beijing or anywhere else, a transit map all pretty much work the same way. It's colored lines, usually to deal with people who may not be able to see the colors. The lines will have designations that'll have letters or numbers or some other form that tells you which line it is. Sometimes they're named. In London, they're named. And then you just figure out which line you're on, you figure out where you are, and you figure out where you're trying to get to, and there you have it. So we have written an algorithm, not just a solution for getting from Wall Street to Rockefeller Center, but we've written an algorithm that allows us to think about how to get from any place to any other place using a transit system. This is a very useful algorithm, and if once you've figured it out, you can use this for the rest of your life. Now, in this case, I told you the algorithm, right? We worked through it together in this video, and you saw me come up with the algorithm, but this is what programming is. It's figuring out how to solve a particular problem and then generalize it so that it will solve that same problem over and over again in the future, anytime that you're given different inputs. And the cool thing is, once you've done it once, you know how to do it anywhere else. This works any city in the world, it works in any transit system, and you could actually change the algorithm only just a little bit, and it works on how to get from one road to another if you're driving, or if you're cycling, or you're in a bike, or you're on a motorcycle, or anything else. So it's a similar algorithm that you're using over and over again in life, and it's all based upon a solution to a problem. And so algorithmic thinking, in the end, is taking a big problem. How do you get from this random place to this random place in New York? I don't know. And then figuring out how to break it down into smaller problems, which is, okay, well, this is on this line and that's on that line, and I don't care about all these other details, and I need to figure out how to get from here to here, and this gets me close, but that doesn't quite connect, and then I need another line that connects me, and okay, I found a solution. That is how you solve problems. And then you generalize it, and you say, well, what did I do? I looked at the first station, I looked at the destination station, and then I figured out if they were connected, and if they were, then I got on the train, and if they weren't, I came back. And you wrote an algorithm. That is an algorithm. It's a set of instructions which, if you follow them, they will get you from one place to another on a transit system. This is the algorithm to navigate subways. Congratulations, you've written your first algorithm. Okay, so next up we're going to spend some time defining different terms. We've used the word algorithm a bunch of times, so let's talk about what it is. An algorithm is a set of sequential steps that is used to solve a problem. So there's a couple of words in there. Steps. Each step has a very specific instruction, and those steps are sequential. And what I mean by that is, in this algorithm, it turns out that if you make the connection first and then try to go to the source, it's not going to work. You have to go to the source first, get on a particular train, go to the connecting point, get off, connect, get onto the next line, and move on. If you do it out of order, it doesn't work. So an algorithm is a sequential set of steps. You follow step 1, then you follow step 2, then you follow step 3. Now, you could argue that whether you start at the beginning, the source, and work your way to the destination, or start at the destination and work your way backwards to the source, you would end up with the same actual solution. And you're right, you could come up with an algorithm that works in the other direction, and that would be fine. In this particular problem, you could solve it either way. When you actually get on the train and execute the steps, you better go in the right direction. But you could come up with a solution to the problem in either direction, starting at the top and working down, or starting at the bottom and working up. It works either direction. So, algorithms should be specific. Computers don't understand gray. Things are either black or white. 0, 1, true, false, power, no power. There is no middle ground with a computer. You have to give it a specific set of instructions. The specific set of instructions have to be understandable by the computer. They have to be written in a computer language eventually. But while you're writing the algorithm, although the language doesn't matter, they still need to be specifically what you want the algorithm to do at every possible moment. So telling it, get on a train and keep going until you get there, is not a specific instruction. You have to tell it, get on the red line going north, and then go till this station and get off, and then transfer to the yellow line, and then get off after one station and then transfer to the orange line. And specifically, you'd have to be more careful about transfer. What does that mean? Well, in some of these stations, it means climbing a stairs or descending a stairs. In other stations, it may mean actually coming out onto the street and crossing the road and going down another stairs to get to the other station. Sometimes they're not even fully connected. So your instructions have to be very, very specific. An algorithm needs to be specific, sequential steps. The third point on here is your algorithm needs to be simple. Now, you might say simple and specific seem like they are kind of in opposition. And you're right, they are. What I mean by simple is not that I said, go to Rockefeller Center. Simple. What I mean is instead that I'm not giving you a bunch of unnecessary detail along the way. This is an algorithm to get from one place to another in a city using a transit system. It in no way speaks about how you buy a ticket for the transit system. It in no way speaks about what you should be wearing while you're on the train. It is just about how to navigate the system. Don't put unnecessary detail into your algorithm that has nothing to do with what it is that you're trying to solve. Each algorithm should be specific to one problem. The last thing on here is it should solve the problem. And that might seem kind of stupid to write down, but you'd be surprised that as you're thinking through an algorithm, how often you would go down a side street and get lost. And what I mean by that is you start looking at the map and you're like, okay, I'm here in Wall Street and I want to go north and, oh, hey, I'm getting off at Times Square. Well, Times Square is cool. It's got all this stuff and I want to see all this stuff in Times Square. And hey, there's this cool museum around the corner and I want to do that and I want to go to Broadway and blah, 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 blah. Okay, well, none of that has anything to do with getting you to Rockefeller Center, which is what you were originally asked to do. So don't go off on a tangent in the middle of the algorithm solving and end up solving some completely different problem. When you're asked to solve a problem, you come back with a solution to that problem. So that's why the last step in an algorithm is that it solves the actual problem that you are being asked to solve. Be careful that what you actually end up producing meets all of the criteria from the person who gave you the problem. And what I mean by this is we're going to give you assignments throughout the semester. And each time we're going to give you very specific instructions on what you need to solve. If you come up with a solution to a different problem and you submit it, you're going to get a 0. Because that's not the problem we asked you to solve. It's cool that you solved that problem and we're very proud of you. But that's not what we asked you to solve. So you have to be careful that you read the actual instruction of what it is that you're being asked to solve and you solved that particular problem. So that's just something to keep in mind as you're, especially at the end of an assignment and you're about to turn it in, you should always ask yourself, did I actually do what they asked me to do? Because along the way, you may have found out all kinds of cool things that sent you down weird paths. Okay, so algorithms contain two different parts, data and instructions. So let's talk about the difference between the two. An instruction is what we originally wrote here. This was our algorithm for navigating subways. Each one of those bullet points is an instruction. Find out what station you're at and which line it's on. That is one instruction, or two, depending on how you break down the comma. And so these are individual instructions. They're executable by the computer, and they're understandable by the human. A separate thing is data. The data would include where you're starting from, where you're ending, what time of day it is, what the weather is, do you have an aversion to crowds, do you have a preference on particular lines, what lines are operating. Those are all things that might need to be fed into the algorithm as what we call input. Input is information that we take and we give the algorithm so that it can produce a specific result. Likewise, at the end, the algorithm returns data back to the user. In that case, the algorithm is returning back to you output, which is information that the computer has created that it's giving back to you. So This program that we are talking about is a program where I can give it a source and a destination and a time of day and a day of week and a couple of other things, and it gives me back a set of specific instructions to get me from point A to point B. Effectively, what we're talking about here is writing something like Google Maps or Apple Maps, which is you type in a source and a destination and you tell it, I want to get from here to here, and then it gives you back information about how to do that. So the input is the source, the destination, the time of day, the day of week, the hour of the day, etc. The output is the actual set of instructions that tell you get on this train, go this way, then turn right, then get off, then transfer to this line, and so on and so forth. And the instructions are the actual computer terms that are doing that work. They're taking the input and finding the correct output for you. Algorithms typically have input, output, and processing. So the inputs, as I say, things you're giving the algorithm, the outputs, things that are coming back, and the processing is what the algorithm is actually doing. The final thing I'll mention about an algorithm is that a big part of writing an algorithm is thinking about everything that could possibly go wrong. If I go back to the map and I tell you, okay, here's your answer. Get on the red line and go north 12 stations and then get off. And I tell you the station you're supposed to get off at is 50th Street, that would probably be enough information for you to understand. I don't know if it's actually 12, you can count them out, whatever. And so you would be able to figure that out and you'd probably get off at about the right station. But if I give those instructions to a robot and I tell it, get on the train and wait 12 stations, what happens if that train is an express and it skips over a station? Well, you're going to notice it because as you go speeding through a station, you're going to be like, that was weird. And then you're going to notice that the next station on the map was not the last one that you thought. So you're going to adjust and you're going to go, okay, well, clearly I just needed to go 11 this time because for whatever reason we skipped over that one. But if you're a computer or a robot, you're just going to follow the instructions you were told to do. And you're going to go 12 stations. And then you're going to get off and be very, very lost. Computers follow instructions absolutely, which is great and also terrible. When you tell them to do something, they're going to do exactly what you tell them to do. Sometimes it won't be what you thought you told them to do, but it is exactly what you actually told them to do. The downside is, if they end up in a state that they don't understand, they don't know what to do with that. And so, as a programmer, as a person who writes algorithms, as a problem solver, a part of your job is to think through everything that could possibly go wrong. Let's take a different example. If you're writing a computer game, and there's a character in the game who can walk around in a world, when they walk into a wall, what's supposed to happen? Well, a developer had to think through that. They had to think about, okay, well, somebody's going to walk up to the wall. And when they walk up to the wall, ideally, it does not let them walk through it, unless that's supposed to be the case. And separately, it should also stop them from walking. But they're still trying to walk if they're holding the joystick in that direction. So I guess you animate them as if they're trying to walk into a wall, is usually what happens. But somebody actually had to think through all of that. What actually happens when that happens? And it's not something you would naturally think through. Because you're like, well, no one walks into walls in the real world, most of the time. But in a video game, it happens all the time, right? You turn a corner and you didn't know that there was a wall there, you walk right into it. So thinking through all the things that can go wrong and enumerating that as part of the algorithm is actually a big part of the job. And it's actually quite difficult because it's not natural. You don't think about everything that could possibly go wrong all day. You'd be a very pessimistic person if you did. Usually you just think through, well, here's how I basically get there, and then you assume it'll all go right. And if it doesn't, you figure it out in real time. Computers can't do that part. If nobody wrote code on what happens when you walk into a wall, the program just crashes. You try walking, and then you get to the wall, you can't walk further, it'll have some kind of a crash condition and the program will end. And that's really bad from a user standpoint. They don't expect that to happen, so you have to be careful that you've thought through all the different things that could happen. All right, so that was algorithm. Next off, we're going to talk about abstraction. The technical definition of abstraction is taking away detail and focusing on just a core problem. It is often described as a lot of different things, so I'm going to give you a much bigger definition that includes other parts that are not technically abstraction, but when you put them all together, they do encompass the general idea. So abstraction is taking a big problem, breaking it into smaller parts,
identifying patterns amongst those smaller parts, grouping the things that are like together, solving the individual parts, building back up to a major solution, an overall solution, and ignoring all of the unnecessary detail as you do it. If you actually take a look at that New York subway map again, you'll notice that the map itself is an abstraction. This is not a map of everything that's in New York. All the buildings are missing, all the roads are mostly missing, all of the detail that is New York is not here. All they really drew was a vague outline of the peninsula and then the actual train lines. And they put in a few more details that they thought might be useful, but like, where is, let's take a random example that I can't think of one. Um, where is the library? I don't know, it's not on here. So, or if it is, I don't see it. Um, where is anything else that's in New York? It's not actually listed on this map. And the reason is because they're abstracting all of that detail away. If they put every single building's name and every single road in New York on here, on top of all of the detail about the transit system, on top of all of the other details about New York, this map would be unreadable. So it's an abstraction. They took the important detail, which is in order for you to get around on the train system, this is what you need to know, and they ignored everything else. Likewise, when we interact with the map, we ignore lots of details as well. If you think about it, I never mentioned the brown line, which seems to run from here up and across this way. Well, it's not relevant to anything that I'm looking at, or the Queens Midtown Tunnel that's right here. I don't care. They're not relevant to me getting from one place to another. So the moment I started looking at this map, I started throwing away details. I noticed that some of the things are going off this way, and I don't need to go that way. There's no particularly good connection to get back over, so clearly that's not the right answer. I can ignore all of that. This is an important part of problem solving, is just being able to focus on the thing that matters and ignore all of the other details. The gray line is irrelevant as well. Here it is right here across this part. Well, that's not going to get me where I need to be, so I don't care. So abstraction is taking something and ignoring all the details that don't matter to you so that you can focus on the thing that you're actually trying to solve. The New York subway map is already an abstraction. It doesn't show all the buildings, and likewise, we further abstract it as we try to problem solve by ignoring parts of it that we know don't matter. As a matter of fact, even what you looked at is not the full map. I just took a snippet of the map and showed you that snippet because everything that's north of there doesn't matter. There's a whole other part of the peninsula, but it's not relevant from getting from that one point to that other point. If you're trying to get somewhere further north, then it's very relevant. But that's not what we were asked in this problem. So abstraction makes problems easier to think about. Your brain can only process so much stuff at once, and the more detail you try to focus on, the harder that gets. So get good about throwing away things that you don't care about. Your brain does this all the time. Every time you look around, your eye sees everything that's in front of you. All the detail about all the bookcases and all the things that are directly in front of you go into your eye. And the name of every, book that's in the bookcase, or the name of, or the color of everything on the walls, all the pictures, all of that detail is there, but it probably doesn't matter to what you're doing. So your brain throws 90% of it away. If you quickly glance around the room and then you get asked a question about something that's behind you, the chances are you're probably going to have only a vague understanding of what's back there. The detail is all thrown away. And that's because your brain can only process a certain amount of stuff. So all the other things that don't matter get thrown away. Your brain abstracts. So you do this all the time in life. When somebody asks you a question like, how did you get here today? How did you get to wherever you are right now? The answer is probably you walked there, you drove there, or whatever else. But that's not a lot of detail, right? So how did you drive there? Well, when I ask that question, how did you get here? I don't expect a long dissertation about how an internal combustion engine works. I just expect you to tell me I drove there. I expect an abstraction. I expect that you're going to take away a lot of unnecessary detail and just tell me the high level, I got in a car and I drove. Okay, great. Because I understand that there was all these other details that happened, like you put your foot on the accelerator, and when there was a stop sign, you came to a stop, hopefully, and when there was a red light, you stopped, and when there was a green light, you went, and you turned the steering wheel, and you knew to do that because there's lines on the road, and you had to figure out where in the line you were supposed to be, and all of these details are in there. They were all necessary in order for you to actually get here, but they're abstracted away because you don't think about them. You just deal with the bigger problem of where am I trying to go right now. Once you understand how to drive, you abstract away the details of how you drive and you only focus on where you're trying to get to. So, problem solving is a lot about abstraction. All right, so next term, software. Software is a computer program that solves a particular problem. Simple as that. It's an algorithm that has been converted into a computer language and implemented with a particular language. So you took an algorithm, you converted it into Java, you entered that in, and you compile it, and you have a running program. Every piece of software that you have ever used in your life, which is every application on your phone, every application on your computer, every website that you've ever visited, all of those are pieces of software that somebody wrote. Somebody somewhere sat down and thought about when you pick up your phone and you press the icon, what is the first thing that you see? And if while that's on the screen you hit the back button, what happens? And if you hit the power button, what happens? And if you click in the middle of the screen, what happens? And then when that has loaded and it gives you the next part of the screen and you click the login button, exactly how is that going to work? And if you type in the right password, what happens? And if you type in the wrong password, what happens? All of that is software that somebody wrote, which is an algorithm that they came up with that explains what's going to happen. And then they wrote it in a language and they shipped it to you. So, software is a computer program which is an implementation of an algorithm in a particular programming language. And the last word, or the last definition here, is going to be computational thinking, which is the title of this PowerPoint presentation and the whole topic this week. Computational thinking is also known as algorithmic thinking, and it is thinking like a programmer. And since a programmer is nothing more than a problem solver, it is thinking like a problem solver. Thinking about how to take a big thing, don't get overwhelmed by it, break it down, and solve it. So let's talk a little bit about how you're going to succeed in this class. If you begin everything that we give you with I don't know, you're not going to succeed. We're going to give you problems, we're going to ask you to think through them, and they're going to be things you've never seen before. They're things that we didn't show you. We're going to show you how to do something. And then we're going to ask you to do something that's slightly different than what we showed you. And the hope is that you can learn from the thing you previously saw how to apply that same skill to the new thing that you haven't seen before. But every problem that we give you in this class is going to be new and unique to you. So there's nothing you can just memorize that's going to solve you or that's going to help you win in this class. And that's a problem for a lot of people. They start off the class and they're like, I just need to know what I need to memorize. Well, that's not going to work. This is a problem-solving class, and all things in computer science are problem-solving. It's not about memorizing a particular thing. This is not like a history class where we give you a book, we ask you to read it, we ask you to understand it, and then we ask you questions about it. There is one correct answer, and it is whatever the book said. That's not how this works at all. Here we're going to show you a problem, we're going to show you how to solve that problem, then we're going to show you another problem, show you how to solve that, and another one, and another one. And then we're going to give you a problem that we've never answered, and we're going to ask you to go figure it out. And there's two ways you can do that. One, you can go look up the answer. And if you do that, you will get an answer, you'll turn it in, you'll get credit on the assignment. Most of the time. The downside is you'll learn nothing. And so we have people who take this class, and they do really great on all the quizzes, and they do really great on all the assignments, and then they bomb the midterm and the final. And usually after the midterm, they come to me and they're like, I don't understand, or test 1, test 2, test 3, depending on whether you're in summer or fall or winter, fall or spring. They come to me and they say, I don't understand. I got 100 on everything and I got a 22 on the midterm. And the answer is, well, you didn't learn anything. Yes, you got an answer turned in, but you didn't actually learn how to do it. So when we gave you another new problem on the midterm, you had no idea how to solve it. Unfortunately, the real answer here is the only way you're going to succeed in this class is to try over and over again until you find a solution. And it's not going to always be fun, if I'm being honest. Problem solving is frustrating because you're going to have to fail many, many times. Unlike with other classes where hopefully you don't ever fail, in this class you're going to be encouraged to fail. You're going to try something and it doesn't work, and then you're going to try something else. And that's how you're going to learn. But that's really frustrating to a lot of people because they're like, well, I didn't know the answer. I don't know how to do this. Why are you asking me to do something that you've never shown me how to do? It's because that's how you learn to problem solve. So it's very important that you don't get overwhelmed and that you don't give up. Those are the two most important things. You just need to start off, break down the problem, figure out which parts you already know how to solve, and then work your way up to the bigger, major solution to the original problem. This is honestly an excellent life skill. It's probably one of the biggest determinations of how you will succeed, or predictors of how you will succeed in your career. If you're very good at this, it's such a hard skill to teach people that this actually is one of the things that will lead you to a successful career. Being able to take problems that are overwhelming, that everybody else doesn't know what to do with, and start to make progress on them is a very difficult skill to find. So, problem solving and not being overwhelmed and just keeping on chugging through it until you get there is a very, very valuable life skill. It will help you in tests. If you start a test and you get to a problem that you don't understand, skip it, move on to the next problem. Work your way through the rest of the test and then come back to it at the end when you have time. And then if you still don't know how to solve it, break it apart and see if there's a part of it that you do know how to solve. And if there is, solve that. And if there isn't, break that apart and see if there's a part of that that you can solve. At worst, you'll get partial credit. And at best, along the way, maybe you'll figure out how to solve the bigger problem. So don't get overwhelmed. Don't give up. Ask lots of questions. That's what we're here for. That's why there are TAs. That's why there are instructors. Keep coming and asking questions. But all this came from the definition of computational thinking, which is a hard thing to explain because computational thinking is problem solving. Breaking down a big problem into smaller parts, practicing how to solve those smaller parts, looking for patterns, putting them back together again, and ignoring all of the unnecessary detail. All right, next up, we're going to talk about the typical software development cycle. People develop new applications, new apps on phones, new games all the time. So, how do they go about doing that? Well, there's a couple of phases to software development. Usually, the first phase involves coming up with a clear understanding of what problem it is that you're trying to solve. So, let's imagine we're going to start a new software company and we're going to build a new whizzy bang game that everyone's going to love in a few years. The first step is to figure out exactly what that game is going to do. Cool is not really a description. We need to know exactly how it's going to work, like what characters are going to be in there, how they're going to talk to each other, how they're going to interact. How do you control the game? Is it a phone game? Is it a console game? Is it a PC game? So we need to think through all of those details and write down a bunch of requirements. The game's going to work on a console. Which console? Which version of which console? Which kind of controller do you have to have? Okay, what exactly is going to happen in the game when you start it? Is it online? Is it only local? Can more than one player play? Can more than two players play? Etc., etc. All of these are requirements that you need to write down. It's super important at the beginning of problem solving that you make sure everybody actually understands what the problem is, because otherwise they'll all be off solving different problems. So this phase of development is to have everybody sit down and figure out what it is that they are trying to solve and write it down so that everybody's on the same page. Once you've got that done, step 2 is to plan the solution. And this is basically writing the algorithm. So you've decided that the game is going to be a first-person shooter and you're going to have bad guys who come at you and whatnot. Exactly how is that going to work? Well, we've gotten requirements as to how it's going to high-level work. Now you're going to actually have to think through all the detail of what that actually means. So how often are the bad guys going to appear? Exactly how do they appear? Did they just spawn? Or did they appear by walking through a doorway? Those are going to be quite different. Do they materialize? Do they, come out of some kind of a spell or whatever it is that they're going to make them appear? So you're going to need to know all those details. As you think through that, you're going to have to figure out how you're going to develop that. What is the actual algorithm that's going to be used to decide how often they appear? For example, if you are in a game where there's bad guys that are appearing, one option is that there's a predetermined number of bad guys in each room. So when you walk into the room, there's 4 bad guys. Or the other option is when you walk into the room, it picks a random number and it puts a random number of bad guys in there. And maybe that random number is based upon your level, or it's based upon what items that you've currently accomplished, or maybe it's just completely random. Sometimes you get 50 people and sometimes you get 1. So those are all things that you're going to have to think through with the algorithm as to exactly how that's going to work. Once you've gotten through that phase, we move on to the coding it phase. So coding it means taking the algorithm that we just got and converting it into a programming language. Now, why didn't we just skip this? Why didn't we just write the algorithm directly in a programming language? Well, the problem is that quite often one company may not use only one language. For example, if you have an Android phone, all of your applications in Android are written in either Kotlin or Java. If you have an iPhone, they're written in a different language. So if somebody puts out an app that works on both Android and iPhone, it actually has to be written twice in two different languages. The algorithm is the same, but the language may be quite different. And so the coding it part may be done by two completely different teams, but the algorithm may be come up with what should have been come up with once, and it works for both coding exercises. So generally, when you're writing stuff, when you're writing an algorithm, you're going to think about it not in a particular language. You're going to think about it at a high level, and then you're later going to convert that into a programming language. The next step is to test what you wrote. So this comes back to my idea that sometimes as you're problem solving, you can get lost. You can go down a bad path. The example was in New York, you were in the middle of figuring out how to get to Rockefeller Center, and then you realize you're in Times Square and you decide, well, let's go to the M&M store. And then you have fun in there for 2 hours, and before you know it, Rockefeller Center is closed. And you're like, okay, well, I never made it. So testing it is to make sure that in the end, after you've coded everything, that what you coded actually met the original requirements. Because if it didn't, you didn't answer the problem that you were asked to answer. So likewise, when you go to turn in your homework, as I mentioned, your assignments, you need to make sure that you actually coded what we asked you to code, otherwise you're not going to get full credit. So you need to get in the habit of testing it and making sure that your algorithm actually does what you think it's going to do. And then the final step on here is document. Over time, you're going to realize that almost every application you use is not written by one person. Usually it's a combination of a lot of people, and they work together to do the development. Maybe different people do some of the problem solving part, other people do some of the coding parts, some people do some of the testing parts, or maybe it's a mixture of people doing all of the above. But over time, those people change. You'll have people who leave the company, you'll have other people who come to the company. And so being able to hand information from one team to another, or from one person to another as they transition into a new role, means that you have to have documentation. So documenting what you're doing is an important step in the typical software development. So we had planning, deciding what it is that we're going to do, writing the algorithm, coding it, testing it, and then documenting what you did. All right, so how do we write the algorithm? If we're not writing it in a specific language, what is it that we're going to do? Well, we've usually three choices for writing an algorithm. The first is we can write it in English, and that's what I did back here with the algorithm to navigate subways. This is in English, and it's a reasonable set of steps. It's fairly concise, but it does have a problem, which is that in general, English is very, well, what's the right word? It's sometimes ambiguous. The same word can mean two different things to two different people. And so that's not great for computers. It works, and at a high level, it's reasonable. It's not unreasonable to write an algorithm in English, but it's maybe not the best choice. So let's look at some other options. We can use a flowchart, which is a diagram that it's a step up from English. Because it's a diagram, you're forced to think through how you would represent it in a diagram. And by doing that, you're going to end up with something that's a bit more specific than English. There are very specific shapes and whatnot, and we'll talk about that, and you'll see an example here in a moment. So flowcharts are one way that you can express an algorithm. The other option is you can write in something called pseudocode. This is something that is not a specific programming language, but kind of like if you took all languages and you merged them together, and then you took away all of the annoying syntax details of the language, you'd end up with pseudocode. It's a general way to express an algorithm without having to care about the details of each of the languages. And what I mean by detail is most programming languages, as I mentioned, require you to put a semicolon at the end of every line. And that's really an important thing to the computer, but it's not something that we as humans really care about. We understand that if it's on the next line, it means it's another line. So to the computer, it's very important, but while you're trying to think through an algorithm, it's really actually distracting. So pseudocode doesn't have semicolons. It doesn't care about spacing. It doesn't care about anything like that. It allows you to write in a programming language without having to think about all of the details of a programming language. All right, so let's do flowcharts first. Each part of a flowchart uses a specific symbol. This symbol at the beginning, the oval one, is the beginning and the end of the algorithm. The arrows are used to transition from one place to another, and they show the relationships between various different states. We have input and output, we have something that's processing, and we have something that's making a decision. An important part of an algorithm is being able to make a decision. If it's snowing and there's 6 feet of snow on the ground, maybe we want to find a subway path that actually gets me there without coming out on the street. If it's sunny and it's 72 degrees, getting out on the street might not be so bad after all. So a decision point would be, is it currently snowing? And then if it is, we go and do one thing. If it's not, we go and do another thing. And that's part of the algorithm. All right, so here's an example of a flowchart. We start at the beginning over here in the start box, and we say, have we passed 1321? This is a yes-no question. If the answer is yes, then congrats, you're done. If the answer is no, then you need to study more, and you need to go back and re-ask, have you now passed it? Okay, well, this is a pretty simple algorithm. You're going to be stuck in this loop, as it were, for a while until you pass the class, and then you'll move on over here. This algorithm doesn't deal with the case that you don't pass 1300, which hopefully that won't be the case, so we're not going to talk about it. All right, so that's a flowchart. You can see that the lines tell you how to get from one place to another. The boxes are the different places that you can be in, and this could be way more complicated. This is obviously a very, very simple one because there's really only 4 boxes on the screen. But you could have one with thousands of boxes that lead you from one place to another, and you could express a very detailed algorithm using this. Pseudocode, as I mentioned, is an informal language that doesn't focus on the syntax, but lets you write something that allows you to express an algorithm without the detail. We'll see more about pseudocode later on as we go through the class, but for now, a very basic example might look something like this. Begin main, which is the beginning of the main algorithm. In here, we're going to print hello world, which is the computer saying hello world to you, and then end main algorithm. All right, so this is 3 lines of code, and it kind of looks like code. You're going to see that this isn't terribly different than if I had written this in Java or in Python, but it's not actual code. You can't put this into a computer and compile it. It won't know what to do with it. But it's close enough that you can use it to discuss an algorithm. Okay, so we're going to take a look at our first bit of computer code. In the next class, we're going to start looking at a robot called Artie, and it allows us to draw stuff with a robot. We're going to give the robot very specific instructions on what we want it to draw, and it will draw it. If you're in an online class, we can't actually physically hand you a robot. So what we're going to do is, for you guys, we're going to do the exact same thing using what's called turtle graphics. Turtle graphics is a way that you can control a turtle, and you can tell the turtle what to do. And it's a very simple language in both cases. They're both identical. Whether you're actually dealing with the robot or whether you're dealing with the turtle graphics, you'll be able to do all the same examples. But basically, this will allow us to draw using instructions. And so as your first assignment, you're going to have to draw something using either turtle graphics or a robot. So in order to do this, I'm going to show you how to use a website called Replit, which is where we're going to get to the turtle graphics. And we're going to focus on that for a moment. So regardless of whether you're in person or online, you're going to follow along with these steps because you're going to need Replit for most of your assignments this semester. And you're also going to use it throughout the rest of your career here at KSU or wherever you may end up. It's a really cool little website that allows you to do fun stuff. So without further ado, click that link, replit.com, and it should bring you to a new window, and it'll prompt you to sign in or sign up. If you've never been to Replit before, which is probably the case, you're going to need to do sign up. It's free. It doesn't cost you anything to do it. You don't have to have any kind of code or anything like that. It's free to everybody on the internet. And so what you're going to do is you're going to log in, probably with your school email address, and pick a password, and then you'll eventually end up at a page that looks something like this. The banner at the top may change over time, but you'll have these create buttons and some other stuff down below. You may also see it look like this depending on how it loaded. There may be a side menu that's visible or not visible. It's made visible by clicking that link up at the top. All right, so take a moment, get logged into Replit, and get to this page. And as you're doing that, I'm going to explain what Replit is. So Replit is a website that lets you program in many different programming languages without actually having to install anything. Generally, if I wanted to program in Java, I would first need to install something called a Java Development Environment, or JDE. A Java development environment, in the case of our class, is going to be something called IntelliJ. So I'd actually have to go download a piece of software off the internet and install it and set it up. And that process often takes a half an hour or more in order to get that installed on your computer. And then if I want to change language and I want to code now suddenly in C sharp, I need a different IDE, or integrated development environment. In this case, it's called Visual Studio. And so again, I'd have to go download Visual Studio and install it. And so it's quite cumbersome to get set up for programming in one language. You have to go off and install a bunch of stuff. What Replit does is it eliminates all of that. It just works in a web browser. You're able to go to a particular web browser, open it up, go to replit.com, and start coding immediately. And it will show you the output of what it is that you've coded. So what we're going to use first for this assignment is something called Python, which is a programming language, with Turtle. And that's because of the ability for us to control the little turtle guy. So Replit gives us access to Python with Turtle, allows us to write commands, and then allows us to see what happens when those commands are run. And so that's pretty cool without having to install anything or do anything, and it's free. The other reason that we like Replit around here is as I do instruct examples in class, I'm going to use Replit for you to be able to see the examples. So I'm going to show you me coding in Replit, and you'll be able to see the output. But the neat part about Replit is everything that we do is automatically public. So if you're in class and you're watching a video, or you're in person in class and you see an example that I do and you want to be able to play with it yourself, all you have to do is grab the URL, the part at the top in the browser that is the address of that Replit. And if you type that into your browser, you'll be able to see the same code that I wrote. And you'll actually be able to fork it so that you get your own copy of it, and then you can make changes to it. So as we go through examples in class, and as we do examples in these videos, be sure to note the URLs for some of the replets that you found particularly challenging or interesting, because you can then go back, grab them, and actually play with them yourself to see how I did something. So it's a great way to be able to go back and see what happened in lecture. All right, so once you've gotten into Replit, you've gotten logged in, and you're at that main screen, the way that you make your first Replit is you hit the plus sign. All right, so if we go back over to our browser window here, the plus sign that I'm talking about is right down here under Create. And since this sometimes moves around because the interface changes every now and again, you can also get to it by pressing that little menu over here on the left and then hitting the Create button up on top. When you do that, you're going to get a window in the center of the screen that loads like that, and it's going to ask you what language do you want to do this in. Your window will look slightly different because you probably don't have a default, but you can see Replit is capable of programming in a lot of different languages. Python, Node.js, C, C++, Ruby, HTML, CSS, JavaScript, Scheme, Go, Rust, Codejar, and so on and so on and so on. It's a very, very long list of things that it's capable of programming in. So it's a really, really capable tool. So the particular thing we want is up in the search templates box, I'm going to type in Python, Python, and I'm going to find the one that says Python with Turtle. And I'm going to click that, and you can see that it filled in Python with Turtle down here, and it says Turtle is a pre-installed Python library that enables users to create pictures and shapes. Perfect, that's what we want. Over on the right-hand side, it automatically fills in a title for you. The title is a random selection of words, so it just picks 3 words. They're completely meaningless, so don't look for any meaning in here. But it created aquamarine sentimental loop fusion, which is complete nonsense. It just has to name every one of your replets, so that's why it picks these 3 random words. You're welcome to name it yourself, so I'm going to call this my first picture. And that's it. I tell it that I want Python with Turtle, I give it a name, and then I hit Create Replit. And after a moment, it's going to bring me to a different screen. It does take a moment, so I will tell you that. Don't look for instant things here. There's a lot going on for this to work, so you just have to be a little bit patient here. All right, so it brings me to this slightly scary looking screen that has all kinds of stuff. There's a white window, a black window, some information in here, and some information over here, and a bunch of buttons all around. This is your integrated development environment where you'll be able to write code for Turtle. So let's go back to the slides and let's take a look at what those different parts mean. So Here's a picture of the window that we were just looking at, and you can see that I labeled them. This center area right here, which is the area that there's an arrow to, this is where you're going to actually write your code. And that's after you've come up with your algorithm, this is actually where you're going to write your code in. When you want to see your results, you're going to look up here in the top right-hand window, and that's going to show you what the algorithm actually caused to happen. Everything else you can pretty much ignore for now. This area down here, don't worry about it. This area over here is for files, doesn't matter for you right now. The only other thing you care about is this run button, which is how you actually tell it to execute the algorithm that you gave it and see the output. So we're going to go back and we're going to make our first replit. We're going to specifically tell it to draw a line. So there are 3 lines of code that you need in order to draw a straight line. You need import turtle, t equals turtle.turtle, parenthesis, parenthesis, t.forward 100. Now, all of that probably makes no sense to you, and that's fine. Don't worry about it. We're just going to type those into the other window and see what happens, and we're going to hit the green button. So over in our other window, I'm going to take away everything that it gave me except for these 2 lines here. So import turtle is the first thing that I was supposed to put in. I'm just going to go back to the slide, and you can see there it is. They already put that in there for me, so I'm just going to leave it. Likewise, the second line told me to say t equals turtle turtle, and that's also in there automatically for me, so I'm just going to leave that. The only thing I really have to change is I need t.forward 100. And there's some other junk down here that they gave me that I'm just going to get rid of. So I'm going to type in what I was told to, which was t.forward, and then parentheses 100. All right, now when you write code, it's very important that you follow exactly what you were told to type. In this case, the t is a lowercase t. Make sure you did a lowercase t. If you do capital, it won't work. The dot is a period. The word forward, there's no space before or after those parentheses, and then there's 100 in there. So always be careful that you go back and you look at exactly what it is that you were told to type and that you did the same thing. Having typed all that in, I'm now going to hit this run button up at the top. And over on the right-hand side in this window here, you can see it drew a line. There it is right there. So what seems to have happened here? The first 2 lines are something that are necessary, and we're going to talk about all this in detail in the next lecture, but don't worry about them, they're always going to be there. Really, the only line of code that I actually wrote was this t.forward 100. And it turns out that for turtle, called t, I'm asking the turtle to move forward 100 spaces. And that's why I got a line that was 100 long, which probably leads to the question, what happens if I told the turtle to go forward 200? Well, let's hit run. Not surprisingly, I get a longer line. And if I ask the turtle to go forward only 20 instead of 200, I'm going to get a much shorter line. So that's it. You've written your first program. You're able to tell the turtle to move in a particular direction for a particular length. There's lots more we're going to do with the turtle and the robots, but this at least gets you to the point where you can start seeing how that works. All right, so at this point, if you are in an online class, you're going to work exclusively in that emulator that we just saw in Replit. If you're in an in-person class, the emulator is still probably the simplest answer, but you may also have the opportunity to work with the RD robot. The RD robot is a little guy that looks like this. Reach him. This is the RD robot. And what RD is able to do is he's able to follow those same instructions. So I could tell RD to move forward 100 spots, and he will draw a line. He actually has a hole for a pen, and the pen goes in through his head, which is a little weird, but there it is. And we'll see how to do all of this in the upcoming lecture. We'll talk about how to program RD. But again, the online version, which is what we just looked at in Replit, does all the same things as RD does. It's just you don't have to physically have an RD with you. So that's going to be it for today's lecture. We're going to pick up here on the next lecture, and we're going to start to see how to program RD and the turtle. See you then.